Hello. Hello. Good morning, sir. Hello. Hello. Good morning. Good morning, Tokunami, sir.
Hello, can you hear me?
Good morning, sir.
Good morning. How are you?
I'm fine, sir. How are you?
Yeah, I'm fine. Thank you.
So we will start at 10. There is still 15 to 20 minutes to start the lecture.
Uh-huh.
So we will start at after 15 to 20 minutes.
Okay. Oh, I will check my slide.
Yeah,
See.
definitely, sir.
Yeah. Hmm. See. Can you see my slide?
Yes.
Oh, okay. Thank you. My slide moving?
Yes, your slides are moving.
Okay. Thank you. Okay. See you later.
Good morning, Dr. Sir. Good morning, beta. Good morning. Good morning, Dr. Takunami.
Good morning.
Abhishek, you can start and
Okay, sir.
Okay. Okay.
Good morning, everyone. I welcome Professor Shinji Tokonami, sir, Professor Rohit Mehra, sir, and all the participants to day 2 of this GIAN course. Today's session will remark the beginning of insightful journey on measurement of techniques of radon isotopes, which will not only expand our theoretical understanding, but will also enhance the practical applications in the realm of environmental radioactivity. So without making more delay, I invite Professor Shinji Tokonami, sir, to start his talk of this J2 of GIAN course.
Okay. Thank you very much. Hello, everyone. Yesterday, we stopped the talk with this slide on measurement of individual radon progeny concentrations. Before going to the next slide, I'd like to review two questions I got yesterday. First one, radon entry into buildings. There are two basic mechanisms, namely diffusion due to the gradient of radon concentration in the environment. Advection caused by the pressure difference between building envelope and outdoor atmosphere. I received a question on radon entry rate. I'd like to introduce some information related to radon entry rate. According to ANSCARE 2000 report, radon entry rate expressed in becquerel per cubic meter hour is, let me see. This physical parameter is dominated by the following parameters. First one, surface area of the walls. Second, radon flux density. It is also influenced by radium-226 concentration and emanation coefficient, density of the material, porosity of dry earth material, and diffusion length in the material, and also the volume of the house. Also, I'd like to introduce the radon entry rate expressed in becquerel per second based on the theoretical approach. Here are dominant parameters for radon entry rate. The first, radon concentration in soil gas under the house at infinite depths. Second, airflow entering the room due to existing pressure difference, which includes gravitational acceleration, height of building, difference in air density determined by the temperature difference between indoors and outdoors, and leakage area, and etc. It is not easy to define the radon entry rate, which includes a lot of physical parameters like this. The second question was on an attached fraction. According to ICRP publication 137, the unattached fraction depends inversely on the ambient particle concentration. The mean values measured in dwellings range between 0.04 and 0.2. Furthermore, measurement of the unattached fraction in indoor workplaces such as schools and offices showed a wide range of values, typically between 0.03 and 0.15. So I would say the typical unattached fraction value is it is 0.08 for indoor workplaces, 0.01 for mines, and 0.15 for tourist cave. So we are going to today's lecture regarding measurement of individual radon concentrations. There are many types of progeny measurement techniques. The first one I would like to introduce is Thibault method. This method was created in 1953. It is one of the earliest measurement methods. The method records the total alpha counting rate at 5, 15, and 30 minutes after the end of the 5-minute sampling, and the 3 radon progeny concentrations are calculated by resolved calculation. Due to its simplicity, it was widely used in the mines. The Thomas method. It was created in 1972. Replacing counting rate at certain time with total counts in different interval. This method records the total alpha counts in 2 to 5, 6 to 20, and 21 to 30 minutes after 5-minute sampling. In order to obtain the higher sensitivity, we have to get a higher flow rate, geometric efficiency, and longer measurement period. Least square method. It was developed by Ravi and Ren in 1969. This method records the total counts from the sample during various periods of time and uses the least square fit for calculation. Numerical solution gives precise results through computer program. Decay method with alpha spectroscopy. This technique is called Maltz method, developed in 1969. This method consists of a proper filter, a silicon semiconductor detector, and MCA. Separate determination of polonium-218 and polonium-214 activities are made by counting at 2 different times, namely 5 minutes and 30 minutes after sampling. This is for measurement of working level. Kuznets method was proposed by Kuznets in 1956. In this method, air is sampled through a filter paper for a short time, commonly 5 or 10 minutes. At least 40 minutes is allowed to elapse after sampling is completed before the count rate from the deposit alpha activity on the filter paper is measured. This method only provides an estimate of working levels and gives no information on the individual progeny concentrations. This method was later modified. I'd like to show you the commercial product of working level monitor, namely Pylon WLX. Features a state-of-the-art solid-state detector and employs sophisticated algorithms to determine the potential alpha energy concentration from radon and thorium progeny in a given volume of air. The detection range is 0.001 to 50 working level. Regarding minimum detectable level, it is 0.001 with 1 hour continuous sampling. I'd like to explain the measurement of an attached and attached fraction. First of all, I'd like to show you the characteristics of an attached fraction. Diffusion coefficient of an attached radon progeny is much larger than that of attached progeny. The diffusion coefficient was first estimated to be 0.054 square centimeter per second, which used to be a single number. Recent investigation had indicated that the unattached progeny is actually an ultra-fine particle or cluster mode, 0.5 to 3 nanometers in diameter, rather than free molecular polonium-218. The higher the aerosol concentration, the lower the unattached radon progeny concentration. The method consists in the sampling of air during a specific period, for example 5 minutes, through an open-faced filter holder that contains a screen and a filter. The filter was used as a backup. A part of the unattached fraction will be collected on the screen, wire screen. The rest of the progeny, namely attached fraction, pass the screen and will be collected on the filter. Two alpha detectors are used simultaneously to measure alpha particles on both the screen and the filter. Look at this. This is wire screen. Unattached radon progeny. Most of unattached progeny are collected on the screen, but attached progeny are collected on the filter. Regarding particle size measurement, the activity size distribution of short-lived radon decay product is a crucial parameter in estimating the radiation dose from inhalation. The amount of location of inhaled activity in the lungs are primarily determined by the particle size. This figure exemplifies the activity size distribution at indoor workplaces. Here is the particle diameter in nanometer, and here is a relative activity. You can find an attached progeny peak. Activity median thermodynamic diameter is 0.09 nanometer. In general, we say an attached progeny. Then we can find the nucleation mode particle, the activity median aerodynamic diameter is 30 nanometers here. Then accumulation mode particle, activity median aerodynamic diameter is 250 nanometers. Coarse mode particles, AMAD, is 5,000 nanometers. These three mode particles we call an attached progeny. So I'd like to explain the graded screen array technique, GSA. The measurable range of the technique is 0.5 to 20 nanometers, which is suitable for ultra-fine progeny measurement. There are 4 to 5 stages for detection. You can see this is a sample of the GSA holder. The GSA holder consists of 5 stainless steel wire screens, 30, 145, 200, 400, and 635 mesh. So we need a different mesh screens. And a backup filter for attached progeny measurement. After 5 minutes sampling, alpha particles on 5 screens and the filter are simultaneously counted using zinc sulfide scintillation detecting system. Counting data are analyzed by the Thomas method. The other technique, screen diffusion battery method. This is suitable for attached progeny. Measurable range 0.5 to 500 nanometers. It is not suitable for coarse mode particles, more than 1 micron. Screen diffusion battery operates on the basis of penetration probabilities through wire mesh screens as a function of particle size. It is assumed that to a good approximation, the deposition of ultrafine particles on the screen is due only to diffusion. Here is a stack filled with metal wire screen in series like this way. Here's the inlet. Air goes through this way. So we measured alpha activity on the filter here. This slide exemplifies the diffusion battery sampler for continuous measurement. As you see, here is a diffusion battery filling with wire screens. Air flows like this way, and penetrated radon progeny are collected on the filter here. On the opposite side, here is a surface, silicon surface barrier detector. Here is a low pressure cascade impactor technique for particle size measurement. I can show you the commercial product, namely Moody. Measurable range 40 to 10,000 nanometers. Moody works by using a series of impactor stages with decreasing nozzle sizes. As air is drawn through the device, particles are deposited onto collection plates at each stage based on their aerodynamic diameter. The low pressure in a cascade impactor decreases the drag force on particles, enabling the collection of smaller particle sizes. Micro orifice uniform deposit impactor. Here is the acronym, Moody. I can show the measurement result of simultaneous particle size measurement by GSA and Moody. Here is the particle diameter, and here is a fractional activity. As you see, there is a peak of unattached progeny. Red line represents polonium-218 activity. Blue lines represent a PAEC, potential alpha energy concentrations. And here is an attached progeny. The model diameter is around 200 to 300 nanometers. This distribution was obtained with a measurement in an underground uranium mine in Japan. I will show you another result of simultaneous particle size measurement by Moody. This distribution was obtained with a measurement in a dwelling, Okinawa, Japan. You see, there was no unattached mode, but we could find nucleation mode particles, also accumulation mode particles, and also we found the cause mode particles. So I'd like to explain the measurement of surface acceleration rate of radon. This is based on the ISO's international standard. The measurement method for estimating the radon surface acceleration rate is based on the following elements. accumulating radon in a radon-free accumulation container applied to the surface under investigation for known duration. Sampling a volume of air representative of the air contained in the accumulation container. Measuring the radon activity concentration in this air sample, calculating the surface acceleration rate. So here is a measuring device. This is the accumulation chamber. You see, we have to estimate the effective volume and contact surface and effective surface. The radon activity concentration in the accumulation container increases over time depending on the surface-related acceleration rate, the volume of the accumulation container, and influencing factors such as inadequate air tightness, namely leakage, and back diffusion. The increase of radon activity concentration can be fitted with an exponential function. Here, look at this figure. C, activity concentration in the accumulation container at time t, Becquerel per cubic meter. S, effective surface, square meter. V, effective volume, cubic meter. Lambda n, decay constant of radon. Lambda b, time constant of back diffusion. Time v, lambda v, time constant of leakage. Phi, surface acceleration rate. This lambda is effective decay constant. Since the background radon activity concentration in the container is close to zero at the beginning of the accumulation process, the initial slope, the curve, is independent of back diffusion. Here. Assuming that radon loss by leakage is negligible, the accumulation phase can be approximated by a linear increase of radon activity concentration in the accumulation container. Therefore, we can rewrite the equation like this. Radon concentration is proportional to time. Here's the application. This figure shows the radon surface acceleration rate using a continuous measurement method by circulation. This is an accumulation container and high density polyethylene tube. Sampling point is here and continuous radon measurement device with pump. Air circulate like this way. another technique. Radon surface acceleration rate using a continuous measurement method by diffusion. Here is a continuous measurement radon measuring device. Here is the detector and accumulation container. It's a passive technique before this is the active technique. I'd like to introduce our technique that is flow-through acceleration rate measurement system. We use AlphaGuard. This is a pulse type ionization chamber. Open air go into this tube, and here is the accumulation container, and air containing radon go into the AlphaGuard, and the air goes out like this way. Also, we measure the carbon dioxide simultaneously. In this flow method, here is the equation to determine the surface radon acceleration rate. Radon acceleration rate, V, sampling flow rate. Capital V, chamber volume. Q, this is air exchange rate, defined as V over capital V. C, radon concentration in chamber after correction. CO, outdoor radon concentration. S, surface area. T, elapsed time from measurement start time. C, CHAM, radon concentration in the accumulation chamber. CBG, background concentration. CF, calibration factor for AlphaGuard. TE, effective time from chamber to AlphaGuard. V1, tube volume. V2, AlphaGuard volume. Here are the critical questions for device selection. When selecting a measurement device, it is essential to think through several factors to ensure optimal performance and alignment with your project needs. What concentration levels do you need to measure? What dynamic changes in concentration are you looking to detect, and over what time frame? What type of analysis are you conducting? Monitoring, screening, or integral measurements? How long will you need to measure without accessing the device? Is the device capable of measuring multiple parameters simultaneously? What are the device's detection limits and range? What are the calibration requirements for the device? So here is some information related to international standards. International standards, I'd like to introduce international standardization for radon-tolon progeny measurements provided by International Standardization Organization, ISO, dealt with methodology. International Electrotechnical Commission, IEC, dealing with equipment. You see, as I told you yesterday, there are many international standards related to radon methodology, radon-tolon progeny methodology. ISO 11665 Part 1, measurement of radioactivity in the environment, air radon 222 Part 1, origins of radon and its short-lived decay products and associated measurement method. It sets general principles. Part 2, integrated measurement method for determining average potential alpha energy concentration of its short-lived decay products. Part 3, spot measurement method of the potential alpha energy concentration of its short-lived decay products. Part 4, integrated measurement method for determining average activity concentration using passive sampling and delayed analysis. Part 5, continuous measurement methods of the activity concentration. Part 6, spot measurement methods of the activity concentration. Part 7, accumulation method for estimating surface acceleration rate. Part 8, methodologies for initial and additional investigations in buildings. Part 9, test methods for acceleration rate of building materials. Part 11, test method for soil gas with sampling at depths. Part 12, determination of the diffusion coefficient in waterproof materials, membrane one-side activity concentration measurement method. Part 13, determination of the diffusion coefficient in waterproof materials, membrane two-side activity concentration measurement method. Here is another number, 16641. This was project by our research group. This technique deals with radon-220, namely tolon. Integrated measurement methods for the determination of the average activity concentration using, of the average activity concentration using passive solid-state nuclear track detectors. So we have another technique for radon in water measurements. 13164, Part 1, General Principles. Part 2, Test Method using Gamma Ray Spectroscopy. Part 3, Test Method using Emanometry, this is degassing technique. Part 4. Test method using two-phase liquid scintillation counting. Regarding IEC standard, this organization has one standard on radon equipment, but which consists of 5 parts, recently 6 parts. Part 1, general principles. Part 2, specific requirements for radon 222 and radon 220 measuring instruments. Part 3, specific requirements for radon decay product measuring instruments. Part 4, equipment of the production of reference atmospheres containing radon isotopes and their decay products, namely STAR. We call this equipment radon chamber. This is common. Part 5, technical report concerning methods of measurement of radon and its decay product in air. We have part 6. This is under development. It covers passive radon monitor system. This project is initiated by my group. So now I'm going to the next topic on the behavior of radon isotopes in the environment. Airborne radon, as you know well, there are variations of indoor radon concentration. Daily variation, seasonal radiation, and entire year variation. See, radon concentration varies with time widely due to many influential factors. Normally, in general, the radon concentration in winter is higher than that in summer. Seasonal variation and correction factors. Indoor domestic radon concentration levels are generally higher in winter than in summer. The increased interior or exterior temperature difference during the heating season, resulting in greater atmospheric pressure differential and enhanced radon ingress via a stack effect. A seasonal correction factor is a multiplying factor applied to a measurement with a duration of 1 or more months in order to derive a meaningful annual average radioactivity concentration. The calculation generally assume periodic, annual, typically sinusoidal variation. It is not recommended to use seasonal correction factors derived in other countries as they may not be representative. If you want to use the seasonal correction factors, first of all, you have to correct the data the whole year. Regarding indoor radon, the effect of ventilation on indoor radon levels is significant, as increased ventilation can reduce radon concentration by diluting indoor air with outdoor air and promoting its escape. Here is example of radon time variation of indoor radon concentration. Here is the radon activity concentration and time of day. Door and windows open, radon concentration decreases rapidly. Then doors and windows are closed, radon concentration increases gradually. Natural ventilation effect is revealed here. Note that the time scale of ventilation is much shorter than the half-life of radon. Equilibrium factor. In an indoor environment, radon progenies can attach to the dust, aerosol particles, walls, or any material found inside a house. As a result, there is no radioactive equilibrium between radon concentration and progenies. We call the equilibrium factor. Typically, equilibrium factor is estimated to be 0.4. There are cases where the equilibrium factor can differ from 0.4 or significantly due to various housing and environmental factors. See? Square. Here, this radon. Triangle. Here, this equivalent radon concentration, that is radon progeny concentration. Using these two parameters, we can calculate the equilibrium factor. This is a broken line. Equilibrium factor is not stable. Equilibrium factor is negatively correlated with the unattached fraction. As you can see, here is equilibrium factor and unattached fraction. When the aerosol particle concentration is high, the unattached fraction is low, and equilibrium factor is relatively high as more of the radon progeny are attached and stay in the air. I'd like to show you the equilibrium factor in various surveys. 18 cities in Canada, number of dwellings more than 10,000 houses. the technique is graph sampling. In the radon concentration, geometric mean 20 becquerel per cubic meter. The EKM factor, the 0.65. Here's the range, 0.2 to 0.82. Ottawa, Canada, 6 by long-term measurement, 51 in the radon concentrations. EKM factor, 0.71. Sweden, 200 houses, 255 houses with short-term measurement. EKM factor 0.44. Pakistan, 138 short-term measurements. Indoor radon concentration, 132 becquerel per cubic meter. EKM factor 0.46. Jordan, 21 by long-term measurement. Indoor radon concentration 144 becquerel per cubic meter. 0.4. In Poland, 54 short-term measurements. 300 becquerel cubic meter for indoor radon concentration. EKM factor 0.32. US, 98 houses with short-term measurements. 260 becquerel per cubic meter for indoor radon concentration. EKM factor 0.25. Czech, 30 houses with short-term measurement. Geometric mean of EKM factor of 0.36. In Germany, 136 houses using short-term measurement, 0.34. Here is Italy. 10 short-term measurements, about 200 houses. The EKM factor range between 0.34 and 0.48. In Greece, about 50 houses with short-term measurements. EKM factor 0.48 in average. So India, 1,265 houses with most long-term measurement. 63 becquerel per cubic meter for indoor radon concentration, and EKM factor is 0.36. In China, 14,593 houses with most short-term measurement. The EKM factor 0.48. Regarding outdoor radon, radon in outdoor air generally does not pose a significant health risk to the public population for two main reasons. Radon exhaled from the ground is rapidly diluted to low concentrations in the open air. Typical outdoor radon concentrations range from 1 to 100 becquerel per cubic meter, with an estimated annual average of approximately 10 becquerel per cubic meter. People people spend only about 20% of their time outdoors. The radiation dose from outdoor radon exposure is significantly smaller by an order of magnitude than the dose from indoor radon exposure. Due to the low perceived risk, there are no specific regulations or recommendations concerning outdoor radon concentrations, and large-scale measurements have primarily focused on indoor radon. Understanding outdoor radon concentrations is important for radiation protection purposes. It provides a baseline to evaluate the anthropogenic contributions to radon exposure. In regions where outdoor radon concentrations are high or approach indoor levels, outdoor radon could contribute more significantly to the overall radon dose. Outdoor radon levels, along with radon flux, will be utilized as input variables to enhance the calculation of the Geogenic Radon Hazard Index (GRHI), which is one of the approaches used for the designation of radon prior areas. Dr. Professor Mera, can I have 10 minutes break?
Yes, sir. Sure, sir.
Okay. See you after 10 minutes.
Yes, sir. We will resume the lecture after 15 minutes.
Okay.
So, dear participants, so we will resume the lectures after 15 minutes. So, in the meanwhile, you can take a break.
Thank you.
Welcome, sir. Professor Tokonami, sir.
Yes,
So we can resume the session if you're okay with it.
yes, I'm okay. Yeah,
Okay, sir. Then, dear participants,
my talk.
we are resuming this session again.
Yeah. Okay. Can you hear me? Okay. Good. So, donor variation in radon concentrations are primarily influenced by changes in atmospheric mixing near the ground. Night and early morning, a positive temperature gradient develops, leading atmospheric stratification and reduced mixing. This condition traps radon near the ground, producing the highest outdoor radon concentration. Noon and afternoon, a negative temperature gradient forms, promoting strong atmospheric mixing. This disperses radon more effectively, leading to the lowest concentrations during these times. Here are the seasonal variations of outdoor radon concentrations. Outdoor radon concentrations are highest in winter, higher concentration in winter than in summer. The variation might be independent of meteorological conditions such as temperature, humidity, or a wind, but is strongly influenced by the air mass. This figure exemplified outdoor radon concentrations over 3 years. Vertical variations of outdoor radon concentrations. Here is a sample of outdoor radon concentrations. A vertical gradient in activity concentration and time variations according to a daily cycle are commonly observed. Regarding outdoor radon service, I could summarize these data in this table. United States, 82 locations, ranges 11 to 110 becquerel per cubic meter. Iowa, 111, annual 7 to 55 becquerel per cubic meter. US, Minnesota, 64, 4 to 55 becquerel per cubic meter. Turkey, 4,730 locations. Winter, 19 to 64 becquerel per cubic meter. In summer, 7 to 28 becquerel per cubic meter. Slovenia, 60 locations. Annual measurement, or 1 year measurement, 3.8 to 41 becquerel per cubic meter. China, 165, 3 to 50 becquerel per cubic meter. In Serbia, 56 locations, less than 244 becquerel per cubic meter. Geometric mean 49 becquerel per cubic meter. England, 69 locations. Annual geometric mean is 6 becquerel per cubic meter, which is similar to Japan. Norway, 82 locations. In winter, 4 to 13. Summer, 8 to 210. Lebanon, 24 locations. Summer, geometric mean 19.7, autumn 16.1, winter 13.4. In Ireland, 18 locations, 4.2 to 7.7 becquerel per cubic meter. Japan, 696 locations, 1.8 to 35.3 becquerel per cubic meter. Germany, 173, 3 to 31 becquerel per cubic meter. East Asia, 20 locations for 3 months, 5.3 to 17 becquerel per cubic meter. Spain, 25 locations, 1.2 to 15.8 becquerel per cubic meter. Regarding equilibrium factor, as in the environment, the equilibrium factor outdoors can vary from one place to another and is also influenced by seasonal and temporal changes. In China, 3,348 sites in 19 provinces. Most short-term measurements. Outdoor radon, 10 becquerel per cubic meter. Equilibrium factor is 0.59. Here is the range 0.17 to 0.75. In Germany's 27 stations, long-term measurement. 0.48. Range 0.34 and 0.62. In Tokyo, just one site, but 1 year continuous monitoring. Annual average 0.51 plus minus 0.12. 0.4 to 0.5 for daytime, 0.5 to 0.6 nighttime, 0.45 to 0.5 spring and summer, 0.5 to 0.6 in autumn and winter. In Poland, short-term measurement. Equilibrium factor 0.22. The range 0.06 to 0.33. In Spain, weekly short-term over 1 year, 13 becquerel per cubic meter for radon indoor outdoor radon concentration. The equilibrium factor is 0.18 plus minus 0.07. One site in New York City, in the United States, 7-year continuous monitoring, 4.2 becquerel per cubic meter for outdoor radon concentration, and the equilibrium factor is 0.67. Soil-borne radon exhalation. Radon exhalation rate is a number of atoms left the unit surface area per unit volume. In other words, we call flux density. Exhalation rate is written by this equation. This is the decay constant of radon. This is emanation coefficient, porosity of the soil, and here is epsilon, porosity of density of the soil and porosity of the soil. Here, this is diffusion length and radium 226 concentration. Emanation coefficient is defined as a ratio between the escaped radon into pore space to the total amount of generated radon. The exhalation process is influenced by many factors, intrinsic factors related to the sample properties itself, extrinsic factors outside medium properties. Here, radon generation by radium decay. This is the geochemical processes. By emanation, radon in soil pore air is present. Radon is dissolved in pore water. And by diffusion, radon are migrated through the soil pores. And by exhalation, influenced by diffusive transport, wind, barometric pressure changes, radon escaped into atmosphere. So by entry, radon enters into the building. Moisture content, it is one of the dominant parameters of radon exhalation rate. Low to moderate water contents. Exhalation increases with water content because increased emanation dominates the process. Saturate point. Beyond a certain water content level, emanation no longer increases significantly. High water contents, diffusion becomes the limiting factor. Radon diffusion through water is much slower than through air, leading to a decrease in exhalation. Here's the moisture content in percent and radon exhalation rate. expressed in millibecquerel per square meter per second. Permeability and porosity in radon acceleration. Permeability and porosity of soil are among the most critical factors of radon concentration due to its short half-life and percentage of radon that escapes from the ground depends partially on its formation depth and the permeability of the soil. Higher radon concentrations are found in soils characterized by higher permeability and porosity because of high radon mobility. The higher permeability, lower permeability. Clay, silt, sandy gravel, and gravel. Radon exhalation from the ground surface affects both indoor and outdoor radon activity concentrations. Therefore, it is important to clarify the exhalation process of radon from the soil to the atmosphere. There are photos of radon exhalation rate measurements. This is a radon in this technique, we measured radon concentration in soils. Here is a passive technique for exhalation rate measurement. Dig a hole and place a passive detector here and cover the lid. Cover the hole with the lid like this. 80 centimeter depth. Waterborne radon. Radon dissolves in water and its solubility increases with decreasing temperature. The concentrations of radon in water may range over several orders of magnitude, generally being highest in well water, intermediate in groundwater, the lowest in surface water. The groundwater is important, being an efficient carrier of radon and possibly a significant secondary source of indoor radon. There is no internationally accepted standards governing the level of radon in drinking water, which are recognized on a worldwide level. Here are recommendations for sampling of radon in water. The sample collection method of water depends on the type and characteristics of the water reservoir. Preventing the leakage of radon is critical during sampling, transportation, and preparation of water samples from sources such as potable water, surface water, or spring water. The sample container should be completely submerged, filled to the top, and sealed without any air bubbles before being removed from the water. Here are techniques for radon. Here is the techniques for measurement of radon in water. This is a continuous radon monitor by degassing technique. Here is a liquid scintillation counting technique. Here is a sample and cocktails here. This is a liquid scintillation cocktail in the vial vessel. The samples here and cocktail, the upper layer. Three hours after sampling, we can obtain the radioactivity concentration. 15 days after sampling, we can estimate radium-226 activity concentration by taking into account the equilibrium between radium-226 and radon-222. Also, here is a gamma spectrometry. The water sample is filled in the glass vial. We measure the gamma ray emitted from the radon progeny. There are radon concentration studies in air, in water. Bangladesh 10 samples using AlphaGuard. Radon concentrations in becquerel per cubic meter, 1.4 to 3.2 becquerel per cubic meter. China, 69 samples using scintillometer, 6 to 127. Finland, 3,000 samples using liquid scintillation counter, 77,000 becquerel per liter. Hungary, using liquid scintillation counter, radon concentration is 100 to 350 becquerel per liter. India, 20 samples using radon 7, 0.5 to 22 becquerel per cubic meter. Iran, 48 samples using the same equipment, radon 7, 4.7 to 31.5 becquerel per liter. Iraq, 20 samples using solid-state nuclear track detectors. This is CR39, 0.36 to 1.5 becquerel per liter. In Germany, 550 samples using gamma spectrometry. Radon concentration ranges 9 to 1,220 becquerel per liter. Malaysia, 27 samples, radon 7, as a detection technique. Radon concentration range from 0.07 to 187. Nigeria, 112 samples, radon 7, as a detecting technique. Radon concentration ranges from 0.95 to 112. Poland, 282 samples using liquid scintillation counter. Radon concentration ranges 0.2 to 1,645 becquerel per liter. Qatar 48 samples using Rado 7, 2.7 to 60.7 becquerel per cubic meter. Saudi Arabia 1025 samples using liquid scintillation counter 0.04 to 67.4. Spain 350 samples, liquid scintillation counter and gamma spectrometry. Radon concentration ranged from 0.224 to 1168 becquerel per cubic meter. In Romania, Transylvania, 1,511 samples using scintillation cell. Radon concentration ranges from 0.05 to 129. Yemen, 19 samples using Rado 7 as detection technique. The radon concentration ranged from 1 to 896 becquerel per liter. In order to reduce the radon in water, we can propose several techniques such as aeration, storage, we keep, hold, and decay, heating and biological process, and granular activated carbon. The choice of the reduction method depends on the factors such as radon concentration in water, treatment cost, system maintenance requirement, and the specific application. Aeration involves spraying or bubbling water with air to release the radon gas into the atmosphere. This is a sample of aeration. Aeration can remove up to 99% of radon from water. Very effective. In granular activated carbon, water passes through a tank filled with granular activated carbon. Radon is trapped in the carbon. The removal efficiency is 70 to 99%. Here is a summary of this topic. Radon levels can vary within the building itself and as well as can fluctuate daily and seasonally. Radon levels can geographically change due to geological features. Radon concentrations are typically lower outdoors due to atmospheric dispersion, but local geological conditions can still cause elevated levels in certain regions. Radon is present in groundwater, especially in areas with high uranium deposits. Radon exhalation is affected by several factors. Now we are going to the next topic on the geometry of radon isotopes.
Thank you very much, sir.
Yes.
Thank you very much, sir, for your such an informative talk.
Yeah.
So, dear participants, if you have any questions, then you can unmute yourself and ask the question. Dear participants, if you have any question, please unmute yourself and you may ask the question.
Well, good morning, Professor Tokunami. It's Dr. Komal here.
Oh,
Yeah.
nice to meet you again.
Yeah, once again, nice to hear you once again with kind guidance of Professor Rohit. And so, I was listening to your lecture 3 that was on radon measurement, and there were slides on comparison of radon in different countries. When we talk about comparison of radon, and that is just a chart, that information, how much concentration in various countries. But suppose we are writing a review paper or something, and we have to give in a comparison data for that. Then different countries have different geological conditions that may have different atmospheric conditions, and many other type sampling may be different. Then how the data of comparison is justified in that case?
Yes, this is a good question, but many researchers use a different type of measurement techniques, so it is not easy to compare, actually. But as I told you in my lecture, there are several international standards on the measurement. In order to keep the reliability, maintain the reliability, I suggest we have to follow the international standard.
Yes, we are following the guidelines of various committees. Yes.
Yeah. So this is my answer. Thank you.
Thank you. Thank you, Doctor.
So there might be one more question from Dr. Mukesh Kumar. He has raised his hand. Hello, Dr. Mukesh Kumar, sir. Are you available there? Dr. Mukesh Kumar, if you have any question, please unmute yourself and you may ask the question. So if any other participant have any question, and you may please ask.
Hello.
Yeah, Bishwajit, you can ask the question.
Hello. Good morning, Professor Tokunami. I have one question we know that some aerosols contaminates radon. So we know the carbons are many effects on environmental effects like warming of global warming and glacier melting of glaciers like that. Is there any harmful effect of radon contamination aerosols on environment?
Yeah. You wrote a question in the chat box, so I understand. To my best knowledge, there's no harmful effect of radon progeny aerosols as a global scale. Actually, from the viewpoint of environmental pollution. But actually, as you know well, radon is the second leading cause of lung cancer This is all.
Yes.
No, no,
Yes, sir.
not similar to carbon. Quite different. It's okay?
Yes, sir. There is a no, not the that is not majorly affected by
No, no,
radon.
no.
Yes, sir. Okay, sir. Thank you, sir.
Yeah. Thank you.
Dear participants, if you have any other question, you may ask. So, Professor Tokanami sir, I think we have
Yes.
no more questions from the participants. So we can conclude this first session of the day here.
Yeah.
And thank you very much for your wonderful talk. And
Thank
we
you.
will resume our the session of next session of this day at 1:30 p.m. Indian Standard Time.
Okay.
So, dear
1 hour and a
participants,
half later.
it's after 1.5 hours.
Yeah. Okay. Yeah.
Yes.
Okay.
So thank you very much, participants, for your patience and active listening during the whole session. So we will meet again at 1:30 p.m. Indian Standard Time at the same same Google Meet link. Thank you very much.
Thank you. See you later. See you again.
Yes, sir. Thank you, sir. Good afternoon, Professor Tokanami, sir.
Yes.
Sir, we will start the session within 15 minutes.
Yeah. Okay. I'm trying to connect. I'm trying to share my slide, but not going well. So,
Sir, your presentation is not full screen. Hello, Tokonami, sir.
yes.
Sir, your presentation is not full screen.
Okay. Can you see my slide?
Sir, I can see your slide, but it is not in full screen mode.
Okay.
So I think you are sharing only window of your screen. Share your entire screen.
Entire screen.
Yes, sir.
Okay.
Yes, sir. Now it is in full screen mode.
Is it clear?
Yeah.
Slide moving?
Yes, sir. Yes, sir. Now it is in
Okay.
full screen mode, sir.
Okay.
So good afternoon, everyone, and welcome back to this session, second session of the day of this GIAN course. So in this lecture today, Professor Tokonami sir will give his talk on dosimetry of radon isotopes. And so without much delay, I invite Professor Tokonami sir to start his talk.
Can you hear me?
Yes, sir. I can hear you,
Okay.
sir.
Can you see my slide?
Yes, sir. I can see your slide.
Okay, thank you. So now I'm deliver a lecture on dosimetry of radon isotopes. To start, we have to confirm the following findings. The direct contribution of radon gas to radiation exposure is relatively low. Short-lived decay products are the main contributors to the radiation exposure. The relation between the radon concentration and the corresponding concentration of radon progeny is expressed through the equilibrium factor. Radon is comparably easier to measure. Its concentration has been used as a surrogate for radon progeny concentration. However, as a majority of the radiation dose originates from radon progeny, caution is necessary when relying solely on radon concentration for dose assessment and control. The dose conversion factors are used to calculate doses from all radionuclides for purposes of radiological protection. Here's important information in ICRP publication 24, Radiation Protection in Uranium and Other Mines. ICRP's first recommendations specifically on radon were published in 1977, focusing on protection in uranium and other mines. It was noted that radium-226 is part of the uranium decay chain, which is found almost everywhere and hence not limited to uranium mines. Noting the rapid development of radon epidemiology, an annual limit on the exposure to radon progeny of 12 working radon months was recommended. ICRP publication 65, the protection against radon-222 at home and at work. In 1993, ICRP publication 65 established the use of action levels in terms of radon concentrations. The recommendations were updated and expanded to include protection at home. Assuming 7,000 hours per year indoors or 2,000 hours per year at work and an equilibrium factor of 0.4. Quantity. Nominal fatal and detriment coefficient at home and at work. Unit millijoule hour per cubic meter. Recommended value 8 times 10 to minus fifth. dose conversion convention, effective dose per unit exposure at home 1.4 millisievert per millijoule hour per cubic meter. Dose conversion factor, a dose conversion convention, effective dose per unit exposure at work is 1.1 millisievert per millijoule hour per cubic meter. Regarding action level in drinks, radon concentration should be set at 200 to 600 becquerel per cubic meter. If we calculate the dose using these radon concentrations, annual effective dose was estimated to be 3 to 10 millisievert per year. Action levels in workplaces. Radon concentration is 500 to 1,500 becquerel per cubic meter. The corresponding annual effective dose was calculated to be 3 to 10 millisievert per year. Occupation annual limit on exposure is 14 millijoule per hour per year, averaged over 5 years. 35 millijoule hour per cubic meter in a single year. Here is an occupational annual limit in terms of radon exposure. ICRP publication 115, Lung Cancer Risk from Radon and Progeny and Statement on Radon. In 2010, ICRP publication 115 updated estimates of the risk of lung cancer associated with exposure to radon and its progeny. This was based on epidemiological results from cohort of miners exposed to low levels of radon and for the first time from studies of lung cancer risk associated to indoor radon. Publication 115 proposed a nominal risk of 5 times 10 to the minus 4 per working level month, replacing ICRP publication 65 value of 2.83 times 10 to minus 4 per working level month. In the statement of radon, the Commission reduced the upper reference level for homes was from 600 becquerel per cubic meter to 300 becquerel per cubic meter. The statement recommended 1,000 becquerel per cubic meter as the entry point for applying occupational radiological protection requirements in existing exposure situations. ICRP publication 126, Radiological Protection Against Radon Exposure. In 2014, recommendations on radon were updated, considering the key scientific findings of ICRP publication 115 and the most recent ICRP principles and methodology. Actually, namely, ICRP Publication 103, the 2007 recommendations of the International Commission on Radiological Protection. An integrated approach for protection against radon exposure in all buildings is recommended. Whatever the purpose of the building, and regardless of whether the occupants are at work or not, the same difference level should be applied and protection be optimized in all circumstances. These recommendations confirmed that authorities should set a national reference level as low as reasonably achievable in the range of 100 to 300 becquerel per cubic meter. Radon concentrations are compared to the reference level to help control radon in homes and most workplaces. ICRP Publication 126 recommended a specific graded approach for workplaces for applying occupational protection requirements, where workers' exposure to radon is not considered as occupational, namely office buildings. The first step, reduce the concentration of radon to a level that is as low as reasonably achievable below the same derived difference level as set for dwellings. The corresponding annual dose is usually lower than that in dwellings because the time spent in workplaces is usually less than the time spent at home. If difficulties are met in the first step, a more realistic approach is recommended as a second step. Second step, optimize protection using the actual parameters of the exposure situation, such as occupancy together with a reference level of the order of 10 millisievert annual effective dose. Despite all reasonable efforts to reduce radon exposure in workplaces, if the exposure persists above the reference level expressed in effective dose, the workers should be considered as occupationally exposed. In such cases, relevant requirements for occupational exposure should be applied. For some types of workplaces, national authorities may decide that exposure of workers to radon should be considered occupational regardless of whether concentrations are above or below a reference level, because the workers are inevitably and substantially exposed to radon. And their exposure to radon is more intimately or obviously related to their work activities. Authorities should consider establishing a national list of such workplaces or work activities, namely mines and other underground workplaces, thermal spas. Regardless of whether workers are considered occupationally exposed, effective doses should be kept below the upper value of the range of for existing exposure situations to 20 millisievert per year. Here's the general approach for the management of radon exposure. Building or location. In the case of drinks, here is a derived reference level, DRL, between 100 and 300 becquerel per cubic meter. In a few cases, at workplaces, such as underground mines, summer spas, it should be considered occupational exposure. In this case, we have to take optimization and we have to take a limit optionally. The measurement, if the derived reference levels, the concentration, if the radon concentration below DRL, based on the ARARA, it will be okay. If the radon concentration is above derived reference level, based on the ARARA, we have to make measurements. In the case of workplaces, measurement, if the radon concentration is below derived reference level, based on the ARARA, it will be okay. But if the radon concentration is above the derived reference level, we have to make a realistic approach based on the ARARA. If the annual dose is below 10 millisievert per year, we go back to the ARARA, and if not, we have to consider the occupational exposure. We have to take optimization and limits, annual limits, optionally. ARARA is as low as reasonably achievable, taking economic and societal circumstances into account. ICRP publication 137. Occupational intakes of radionuclides, Part 3. Although protection against radon is primarily based on measurement and control of levels of exposure, those estimates are required in certain situations for workers. Those estimates are of value for protection purposes when workers are exposed to more than one source of radiation, as is the case for underground miners. In addition, those estimates are required for comparing sources of public exposure. Using the nominal risk coefficient from ICRP publication 115, 1.4 times 10 to the minus 4 per millijoule hour per cubic meter. And ICRP publication 103 determinant values are those conversion convention value of 3.3 millisievert per millijoule hour per cubic meter. For others is obtained. This is fundamentally based on epidemiological evidence. On the other hand, using the dosimetric models, the dose coefficient are 3.3 per millijoule hour per cubic meter for workers in mines and 4 millisievert per millijoule hour per cubic meter for sedentary office workers. Using the same methodology, the dose coefficient for exposure in homes is 3.7 millisievert per millijoule hour per cubic meter. For touristscapes and indoor workplaces where workers are assumed to spend 2/3 of time in exercise, the dose coefficient are 6.7 and 5.7 millisievert per millijoule hour per cubic meter, respectively. There is remarkable consistency between coefficients obtained by dosimetric calculations and conversion coefficient based on epidemiological comparisons. Taking account of both methods and their associated uncertainties, the following rounded dose coefficient present in ICRP publication 137 are recommended. That is to say, for building and underground mines, in most circumstances, the recommended dose coefficient is 3 millisievert per millijoule hour per cubic meter. Approximately 10 millisievert per working level month. The corresponding dose coefficient expressed in terms of radon-222 gas exposure depends on the equilibrium factor between radon gas and its progeny. Using the standard assumptions of equilibrium factor of 0.4 for most indoor situations, this dose coefficient corresponds to 6.7 times 10 to minus 6 millisievert per Becquerel hour per cubic meter. While ICRP publication 137 does not specifically address public exposures, it is intended that this same dose coefficient applies to exposures in homes. Dose coefficient for radionuclide intakes by members of the public will be published in due course and will include radon. Using this dose coefficient, exposure to radon at the upper value of the national reference level of 300 becquerel per cubic meter recommended in ICRP publication 126 correspond to an annual effective dose of 4 millisievert at work and 14 millisievert at home. For the specific situations of indoor work involving substantial physical activity and exposure in tourist caves, the recommended dose coefficient is 6 millisievert per millijoule hour per cubic meter, approximately 20 millisievert per working level month. In cases where aerosol characteristics are significantly different from typical conditions, where sufficient reliable aerosol data are available and estimated dose warrant more detailed consideration, it is possible to calculate site-specific dose coefficient using data provided in ICRP publication 137. Here is a flowchart of effective dose due to inhalation of radon. First, we obtained annual radon concentration in becquerel per cubic meter. Using the proper equilibrium factor, typical value is 0.4, we can obtain the annual equilibrium equivalent radon concentrations in becquerel per cubic meter. By multiplying the occupancy factors, namely 7,000 hours per year indoors, we will get the time integrated equilibrium equivalent radon concentrations, becquerel per cubic meter hour. Then, when the dose conversion factor is assigned, we can obtain the annual effective dose in millisievert per year. Dose conversion factor is affected by particle size of radon progeny, biological parameters, and etc. For dose assessment, equilibrium factor depends on the ventilation rate of the houses, indoor air quality, activities of residents, and so on. Dose conversion factor includes the following process and condition: deposition of radon progeny aerosols in the respiratory tract. The particle size is a dominant parameter. Absorption, lung to blood. Biokinetics. Dose calculation with radiation weighting factor, tissue weighting factor, and assigning partition for tissue weighting factor among thoracic region, capital BB, BB, and AI. There are challenges in lung dosimetry of radon progeny result from non-uniformity of radon progeny deposition within the bronchial region and among bronchial airway surfaces. Short range of alpha particles in relation to the non-uniform distribution of sensitive target cells in bronchial epithelium. Relationship between stopping power and alpha particle range. The lung dosimetry model comprises 5 submodels: morphometric lung model, detailing anatomical structure of the lung in terms of the number of airway generations and their characteristics such as diameter, length, branching, and gravity angles. Second, respiratory physiology model defines the breathing patterns related to different physical activities. Particle deposition model comprises extrathoracic, bronchial, and pulmonary deposition efficiencies, physical deposition mechanisms in cylindrical airways, and related analytical deposition equation for specific flow patterns. Bronchial clearance model comprises mucocerebral mucociliary clearance and transport into the blood. Dosimetric model specifies the geometry of alpha particle interactions with sensitive target cells at different depths in bronchial epithelium. There are models currently used. Models where the absorbed dose to sensitive target cells in bronchial airway generations is calculated, such as deterministic and stochastic airway generation models. They are sometimes called anatomical or biological models. Semi-empirical compartment models, such as ICRP human respiratory tract model, combine many airway generations into components to simplify those calculations. They are sometimes called pharmacokinetic or biokinetic models. What is airway generation model? Lung is made up of airways co-generation. Trachea is regeneration zero. This is a straight duct with ring structure. Here. Generation zero. The upper bronchial consists of generations 1 to 16. 1 to 16. This is a series of branching smooth tube. Alveoli start appearing at generation 17. Airways are much smaller than the wall with alveoli is no longer smooth, as you can see, like this. Human respiratory tract is composed of three functional regions: extrathoracic region, nose, mouth, and pharynx. A filter to protect the lung. Tracheobronchial region, capital BB and BB. Bronchial and bronchiolar airways to distribute inhaled air to the gas exchange region. Alveoli interstitial region. Gas exchange between lung and blood takes place via alveoli. Inhaled radon and radon progeny may be transferred to the other organs of human body via the bloodstream. This is a schematic model of location of sensitive target cells, basal and secretory cells throughout the bronchial epithelium in capital BB region. Sensitive target cells in bronchial epithelium are defined as the cells receiving energy from radiation that lead to development of lung cancer. The range of 6 MeV alpha particle from polonium-218 fluid of tissue is 48 micron, and that for 7.7 MeV, alpha particle of polonium-214 is 71 microns. Target cells, basal cells, and secretory cells. There are personal parameters affecting lung dosimetry. The most important personal factors are extrathoracic, namely nasal and oral geometry, anatomical structure and linear airway dimensions of lung, physical activities, and related breathing parameters. Bronchial clearance velocities, spatial distribution and frequency of sensitive target cells in bronchial epithelium, human subject age, and smoking status. On the other hand, the most important environmental factors are attached and unattached particle size distributions, attached and unattached fractions, radon progeny activity concentrations, and their nuclide-specific distributions. There is a difference between ICRP model and airway generation model. While the ICRP model can be applied to the inhalation of any radionuclide, the generation-based models were specifically developed for inhaled radon progeny. The differences are the lung structure consists of only three components: the large bronchial airways, capital BB, the smaller bronchial airways, BB, and alveolar interstitial region, AI. Deposition fractions in tracheobronchial, TV, and AI components are obtained by appropriate fits to human experimental data and expressed as functions of particle and flow parameters. It is a semi-empirical. The clearance pathways and related half times refer to the whole component and not to single airway generations. Doses to bronchial target cells are computed for the total alpha activity in a given compartment rather than for steady-state surface activities in individual cylindrical airway generations. Here is a comparison of radon progeny absorbed dose coefficient in bronchial, capital BB, bronchiolar, and alveolar interstitial airways by three lung dosimetry models. The region and mode, unattached mode, attached mode. Here the computer mode calculation code to determine radon progeny dose, absorbed dose per working level months. There are three types of calculation codes. RADP IMBA is ICRP Human Respiratory Tract Model, Deterministic Regional Compartment Model, RADOS, Deterministic Airway Generation Model, ideal dose, Stochastic Airway Generation Model. The comparison, here is the comparison of the lung cancer risk per unit exposure based on dosimetric and epidemiological approaches. Here is the exposure expressed in working level months. Using the lung model parameters and aerosol parameters, we will obtain the absorbed lung dose. Then, considering radiation rating factor, tissue rating factor, and assigning partition for tissue rating factor among thoracic region, we will get the effective dose. Then, with the determined adjusted nominal risk coefficient, we will obtain the risk. This flow represents a dosimetric approach. On the right side, after getting the exposure values using the risk model, we just get a risk based on the epidemiology. This is the epidemiological approaches. Tissue rating factors and respiratory tract regions, functional regions of human respiratory tract model, extrathoracic region included in remaining tissues 0.12 as a totally 14 tissues. The corresponding value is quite small at the extrathoracic region. Tracheobronchial region, namely bronchial and bronchiolar airways and alveoli interstitial region, the tissue rating factor of 0.12 for lung is equally divided into three regions, 0.333, 0.333, and 0.333. This figure shows a regional deposition as a function particle size calculated with a human respiratory tract model for a standard worker. Blue continuous line, bronchial region, continuous line, bronchiolar region, dash line, half extrathoracic equals half of the deposition of extrathoracic region. Approximating the deposition during the inhalation phase. Filtration in the ET region affects the fraction of particles entering the lung. This region can play a role of filtration of radon progeny aerosols. In this figure, unit density and unit shape factor were assumed. Here is a particle size, particle diameter in nanometer, and regional deposition. As you see, unattached mode around here, unattached mode, here's a nucleation mode. This is a accumulation mode. Then here is the coarse mode. I summarized those conversion factors in ICRP publications. This is ICRP publication 50, 1987. 6.4 indoors, 8.9 outdoors. The unit is milliworking level, millisievert per working level mass. In 1993, from publication, ICRP publication 65, 5 at work, 4 at home. 1994, according to ICRP publication 66, based on the human respiratory tract model, this calculation provides 13.4 millisievert per working level mass at work. Just 1 year after, there was a large difference between the two. Here, this is the epidemiological approach, and here is a dosimetric approach. 2000, using ICRP publication 66 model, they calculated the dose conversion factor with 15 millisievert per working level months at home. There are 3 times difference between the two approaches. Then 2001, my colleague, they calculated dose conversion factor using ICRP publication 66 model, 13.7 at work, 14.3 at home. After 9 years, ICRP publication of 115 gave new value based on the epidemiological data. 9 millisievert at work, 7 millisievert per working level month at home. In 2014, ICRP publication 126, 12 millisievert per working level month at work, 9 millisievert per working level month at home. The most latest publication, ICRP publication 137, based on the dosimetric approach, this publication gave us 10 millisievert per working level month at work. These are very similar each other. Maybe I have to finish lecture today. Hello?
Hello.
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 Yes. I will stop here and
Yeah,
I'll continue
sure, sure.
tomorrow.
So we'll be meeting Dr. Tokonami tomorrow morning at Indian Standard Time, 10 a.m. Like today we started.
Yep. Yes.
Yeah,
So thank you very much, Professor Tokonami sir, for sharing your expertise and perspectives for enriching our understanding of dosimetry of radon and its isotopes. Uh, if participants have any question, then they may ask. So dear participants, if you have any question, please
So
unmute
I,
yourself.
I I have one particular question, Dr. Tokonami. Like these models which you were discussing, the dose conversion factors which you have calculated, means how they are different from the hair compartment model and Bernard's model. Means,
Okay.
tissue equivalent
May-
factors are different rather used in these models, or they are the similar one?
It's similar.
They are the similar
Similar.
one.
Yeah. But depending on the default value.
Okay.
Yeah.
So anyone from the audience? Abhishek, if you have any question,
No, so thank you very much, sir.
so then we can thank the speaker and we will start our next session at around 2:30. So thank you, Dr. Tokonami, for giving your valuable
Thank you.
time. So we will
Thank
be
you.
see you tomorrow. Thank
See you
you.
tomorrow.
Thank you.
Thank you very much.
Thank you.
So dear participants, we can have a break of 5 to 10 minutes and we will meet at 2:30 for our next lecture.
Thank you. Sure, sure. So we will be meeting for the next lecture at 2:30. Just 5 to 10 minutes break is there. So after this break, we will be starting the final session of this day. So I will be joining at around 2:30.
Okay, sir. Good afternoon, sir. Shall we start? Should we start, sir?
Am I audible now?
Yes, sir. You are audible, sir.
So should we start?
Yes, sir. We can start. So, welcome everyone. After waiting a short break, so our next speaker, Professor Rohit Mehra sir, is with us. So, invite Professor Rohit Mehra sir to deliver his talk on impact of fly ash concentration in the cement for an enhanced level of radioactivity. Professor Rohit Mehra sir.
Yeah. Good afternoon, all of you, and I hope that you might have taken your lunch, and it's very difficult to attend the lectures after lunch. So, Dr. Tokunami has given you an idea about the different models which are being used for the calculation of radiation doses. So, this topic we have kept as a little bit different type of a topic, where actually instead of directly dealing with the radioactivity, we are having a case study where we were assessing the impact of use of fly ash in the cement and how it has enhanced the level of radioactivity in the environment. Because yesterday during my lecture I was discussing that the building materials plays a very important role in the concentration of natural radioactivity, because the choice of the building material is very particular. Especially it depends upon the architect, it depends upon the civil engineer, it depends upon the owner, that what type of building material he or she is going to use for the construction of their dwellings or houses or offices. And depending upon the choice of the building materials, sometimes knowingly or sometimes unknowingly, we get the enhanced level of radioactivity. Like yesterday, I was discussing, if you use granites, so granites are generally naturally radioactive in nature. So the more the granite is used in the buildings, more exposure is there. So more exposure doesn't mean that it will cross the limits or the safe limits, but it will enhance the doses which are received by the residents due to the natural as well as due to some anthropogenic activities. So when we were discussing that how we are being exposed, the main exposure was due to the natural radioactivity, and the second was due to the anthropogenic activities. So the choice of building material also contribute to the type of anthropogenic activities. The reason is, if you use a building material like granite, which is having more concentration, so you are more exposed to radiations. So that is why it is very important to understand that what is fly ash, how it is being mixed in the cement. The reason for it is, India is basically a thermal based country where most of our energy needs are done with the help of thermal or the hydel electricity. So still we are not in that race where most of the energy needs are done with the help of a nuclear energy, we are still using our conventional sources as hydroelectricity and thermal power plants to serve our needs for the energy requirements. Now, if you talk about commercial availability of cement, once you go for purchase of cement from the market, you cannot get OPC, that is the ordinary Portland cement, which is a pure cement, you could say, in terms of layman's language. I'm not teaching to the civil engineer, so quite possible civil engineers might be understanding it in a better manner, that what is OPC and what is PPC, Pozzolanic Portland cement and ordinary Portland cement. But just for your knowledge sake, I could tell you that OPC is not directly commercially available in the market. Whatever the cement you get from the market for manufacturing of your houses or dwellings or offices or whatever you are going to construct, you will be getting a PPC cement, that is a Pozzolanic Portland cement. And the best Pozzolanic material which is used nowadays is the fly ash. So the cement which you are getting from the market, it contains nearly 30 to 45% of fly ash and nearly 45 to 70% of the cement. So it is a mixture of OPC plus fly ash. So OPC is a pure cement which is available in different grades like OPC 33, OPC 43, OPC 53 grades. So, but it is available only to some of the construction agencies like CPWD, B&R and other agencies. So commercially, if you want to purchase the cement, you will get only the PPC, that is the Pozzolanic Portland cement. So why the fly ash is being preferred as a Pozzolan material? The reason was there was a problem with India that we were the thermal based country, and in the thermal power generation, the basic raw material was the coal. And once you use the basic raw material as a coal in the thermal power plants, the residue of the coal is the fly ash. So fly ash, you could say, is produced by the coal fired power plants, and it provides an excellent prime material which is used in the blended cement, even in the mosaic tiles or hollow blocks for the construction purposes. And most importantly, it is free of cost available. So if you go for a concrete mix design, so in civil engineering language, concrete mix design is basically a combination of coarse aggregates, which we call bajri in our terminology, then admixture, then water, then the cement, and then the fine aggregates of sands, depending upon what type of concrete we are going to prepare. Now, the fly ash as a civil engineering part, if you say, will be considered as the best Pozzolanic admixture. So Pozzolanic admixtures or the mineral admixtures are those materials which in itself does not possess any cementanious qualities, but they show cementanious property in their finally divided form when they are combined with calcium hydroxides. So means if you mix these Pozzolanic materials admixtures with the cement, they provide a very good binding capacity. So that is why once it was decided by the government of India, especially to commercially sell the cement only as a PPC cement, two problems were solved. The first one, as the dumping of fly ash was a problem and we are having a lot of residue of fly ash from our thermal power plants, so a solution was provided that fly ash will be taken by the cement companies during the manufacturing of cement, and commercially they will sell only the PPC cement, which is containing nearly 30 to 45% of fly ash. Second thing, there is another property which was solved, that the binding capacity in a civil engineering aspect, if you say, of the cement got enhanced with the use of fly ash. So otherwise it enhances the strength. The reason is it reduces some permeabilities. So the durability property of the concrete also increases. Now, based upon this, there were a lot of news in the different newspapers, on the news channels, that now the government is promoting the fly ash materials as a building materials. So the first reason was, I have already told you that the dumping of fly ash was a problem with the government, but with the choice of fly ash in the cement, that problem got solved. And second, their strength got better, the leaching properties got decreased. So the tiles which were not sticking to the actually OPC cements during their panel work or butch work, now they are more sticky to the cements. So that enhances some of the constructional parameters. So that is why the government give lot of initiatives to use the fly ash in the cements. Now these are few benefits. Like I have already told you that it is a residue which is available as a end product of the burning of coal in the thermal power plants. So it is highly economical. So another is, it is environmentally friendly, as the waste material from the industries are effectively being used to create quality building materials. So it has very small particles, so it reduces the permeability of the concrete. So it can add or gather strength to the building. The concrete mixtures generate a very low heat of hydration, which prevents thermal cracking also. So if you are using calcium carbonate, then a lot of heat is generated. So if you are using fly ash, the heat parameters are reduced. So you could imagine that cracks will not be developed. So it is resistant to the acidic and the sulfate attacks. Then the shrinkage of fly ash concrete is very less, because permeability has already been taken care of, and now the shrinkage is not there. There are no pore spaces available in the concrete, so shrinkage reduces. So it also gives a very good durability and strength to the cement. So once the discussions were going on, so it was achieved that fly ash is the best use as a pozzolanic material, and definitely it is solving the major problem of India, where we are having 72% of electricity needs done or catered with the help of thermal power plants. So nearly, if you see the data, so it produces 90 million tons per year in India. That is, a fly ash is produced. So to dump this fly ash, there was a problem. With the choice of fly ash in the cement, that problem got solved. Second is, as it is the residue of the coal, so depending upon the properties or its size or finer particle size, the permeability get reduced and concrete got lot of strength. So this was the positive aspect of use of fly ash in the PPC cements. So when we were discussing these parameters with our peer colleagues of the Department of Civil Engineering, so there was no cons all pros were there for the use of fly ash in the cement. So then we got an idea that some of the papers which we studied from our literature, that in and around some thermal power plants, there was enhanced level of radioactivity. So we were surprised to note it down that why there is increase of radioactivity concentration in and around some thermal power plants. From the literature, there are a lot of papers which are available. So what we tried that we tried to locate some of the articles, we tried to locate some of the studies which have been conducted in various countries also. And we found that the scientists have analyzed that cement containing fly ash has more radium, thorium, and potassium activity concentration. So that was a big concern for us, for our group. And we started a pilot project with the help of civil engineering department of our institute, because I have already told you that commercially it is very difficult to get the OPC cement, but for some construction agencies like CPWD, B&R, PWD, the OPC is available. And with the help of our civil engineering colleagues, we tried to catch up some OPC samples of different cement companies and then compare it with the different mixtures of fly ash in our own lab. So I will be presenting those results to you also, where we will be dealing with the how this mixing of fly ash in the OPC cement has enhanced the level of radioactivity. That is the con for the use of fly ash. So we were discussing the pros only as a civil engineering aspect, but there are cons, and I will show you some of the results, so which are very interesting and which are very informative also, like how the different concentrations have enhanced the level of radium, thorium, and potassium. Though deeper studies are being required to reach to the final conclusions, like if radium, thorium, potassium activities are increasing, that depends upon the quality of the coal also. Because it's not the case that for every similar type of admixture in the ratio, say 10% of fly ash and 90% OPC, 20% of fly ash and 80% of OPC, 30% of fly ash and 70% of OPC will give us same results. It is not there. The reason is the quality and the grading of fly ash is different from the different thermal power plants. So we have collected samples from different thermal power plants, and we found that the same ratio gives a different results. So that leads to another enhanced studies that the type of the coal which is being used in those thermal power plants, that is also responsible, because fly ash is only the residue of the coal. So if we are having a different concentration, means for a similar concentration, if we are having a different concentration of level of radioactivity, that may be only due to the reason that the coal is of different quality which is being used in different thermal power plants. So this charts gives you basically an idea which you might be very much aware now, and that worldwide annual effective dose from the external exposure is around 0.9, which out of which 0.4 millisieverts comes from cosmic and 0.5 from the terrestrial gamma rays. And then from the inhalation, that is mainly the radon, nearly 50 to 55% contribution of the total annual average effective dose. That is 1.2 millisievert is only from inhalation of radon. And then due to ingestion, you get around 0.3 millisieverts of doses. So in totality, it is on an average 2.4 millisieverts per year. That is the world average. So the third column of the table gives you a typical ranges that cosmic rays world average is zero point 0.4, but it ranges from zero point 0.3 to 1. That is ranges from sea level to high ground elevations. Similarly, for terrestrial gamma rays, which is zero point 0.5 as a worldwide average annual effective dose, zero point 0.5 millisieverts, it ranges from zero point 0.3 to zero point 0.6, depending upon the radionuclides composition of the soil and the building materials which you are using. And the third, that is inhalation, which we generally have a average value of 1.2, but it ranges from zero point 0.2 to 10. So it's a big range. The reason is, I have already told you that it is mostly due to the accumulation of radon gas, and that depends upon different dwellings. So dwellings with better ventilation conditions have lesser accumulations. The dwellings or houses with bad ventilation conditions have a higher concentration of radon. So the choice of the building materials along with the ventilations plays a very important role while constructions. Similarly, for ingestion, it ranges from zero point 0.2 to zero point 0.8. So ingestion depends upon the type or composition of food and drinking water which we are taking from day-to-day activities, and the worldwide average is around zero point 0.3. So if you just combine all 0.4, 0.5, 1.2 and zero point 0.3, so you get a total worldwide average annual effective dose of 2.4 millisievert, out of which nearly 1.2 comes from radon only. So this is, of course, the table which we discussed yesterday, that how this millisievert of exposure gives you an effect. So it gives you a different types of effects on the different types of exposures from 50 millisievert to 20,000 millisievert. The table is showing you an idea. So once you go for an X-ray also, so you have been exposed to 0.2 millisieverts of radiation dose. So generally in India, we don't have our radiation record monitoring system, which in European countries, it is very much compulsory to give the radiation exposure to the patient once he has undergone any test, maybe a X-ray, maybe a CT scan, maybe a PET scan. So every time, whenever the patient has undergone an X-ray or a CT or a PET, or even MRI, though MRI gives a very lesser amount of radiations because it is a magnetic resonance imaging. So, but X-rays and CT, which are the advanced form of X-rays, they give a high level of radiation doses along with the PET scans. So, patient should be given a proper record that during a annual year, how much he has been exposed to the radiations due to the medical purposes. But still, we are at a very initial stage in India. We don't have even right now any regulations or standard authority which could lead to the compulsory disclosure of radiation exposure given to the patient during an X-ray. So though we are having some controlling agencies which publish guidelines as per the guidelines issued by the ICRP to the radiological institutes, there is a agency, Atomic Energy Regulatory Board, which have some guidelines or does a control or monitoring of these radiation institutes or radiation centers where X-rays or CTs are being performed. But still, we don't have a particular law that if I have been given a CT scan or I have been under the treatment of a CT, it is my right that I should be given an idea that I've been exposed to this much of radiation, so that I can have my annual record that how much I have been exposed. Now, these are the two famous series which you might have studied during your BSc classes also, or graduation classes also, uh, where we use the decay series or thorium series and uranium series. And these blue arrows pointing towards the left gives you an alpha decay, and a move color arrow pointing towards the upper side gives you a beta decay, and a red color arrow indicates that during the decay series there is a gamma ray which is being emitted out. So these are very famous series which we call as a uranium and thorium series, which every physicist or every radiation physicist should know. And if you see yesterday, like when Dr. Tokonami was telling you that thoron is also very important nowadays. So from the upper series, thorium series, you see from the thorium, once alpha decay occurs, we get a radium 228. Then with the beta decay, we again get actinium 228. Then thorium 228 with the again beta decay and a gamma ray emission. And if you see, there is a radon 220, that is the isotope radon which we call as thoron. So it is very important, and that is why it is from the decay series of thorium, so we call it as a thoron also. Now in the uranium series, if you see from the radium 226, so uranium has a half-life of around 4.5 million years, 4,500 million years rather. So that is the age of Earth, 4.5 into 10 raised to power 9 years. Or you could imagine that from this radium, the alpha decay occurs to form a radon. And yesterday we have discussed that from this radon, once again the alpha decay occurs, we get the daughter products polonium 214 and 218, which are responsible for causing the natural radiation exposure to the human beings. So that is why these series are very important to understand. These series are very important to remember. So any person who is working, especially the PhD students who are working in these areas, so you should have an idea. And there is a nomenclature to write these series also. Means once the alpha decay occurs, it should point towards left downward. Beta decay occurs left upward, and then gamma, there is no change because there is no change in the atomic number and atomic weight. Now what we have done in our lab, that we have collected some of the samples and we tried to measure the radium, thorium and potassium concentration. So there are different choices of your instrumentations. You could measure it with the gamma ray spectroscopy using HPG, that is high purity germanium detectors, or you can go with the sodium iodide scintillation counter. So which is based upon the scintillating materials. Generally sodium iodide is thallium doped, so to have more enhanced scintillation materials. So in our lab, we are having the scintillating materials, but we are having collaborative institutes where we are having HPG also, and we are performing some intercomparison activities between choice of different techniques also. So this is the specification for our detector, and if you could see from the monitor, you might be seeing some of the peaks. Across x-axis, these are the energies, and across y-axis, these are the counts. Now across x-axis, if you are having a peak, so that peaks corresponding to a particular energy indicates that an element corresponding to that particular energy is present. Suppose you are getting a peak for 1461 keV of energy. So that indicates 1461 keV of energy or gamma ray is being emitted out, and element containing to that 1461 keV is present. So which is generally the potassium. So these are the specifications of the instrument, which you rather I won't discuss in details because These are the standard specifications, and these are the volumetric activity measurements, like how much you could concentrate or measure. Now, the samples were collected from different locations and areas, and we generally do the grinding of those samples, and then we do the sieving of those samples with the help of 150 micron mesh size. So what is the reason behind this is to make the samples very fine, so that the pores which are present in the samples, they get reduced and moisture get exposed. So then we remove the moisture even by drying those samples in the sun, or even sometimes in the um, furnaces at around 100 degrees Celsius for 2 or 3 hours. Then we keep those samples packed in the containers to attain some radioactive equilibrium. So preferable time is around 1 month, so that the radioactive equilibrium is attained. And we packed those samples like this with the different concentration of fly ash. We started with the pure OPC, that is 0% concentration of fly ash. Then we started with the 90% by mass. It's by mass, it's by weight only. 90% of OPC, 10% of fly ash. Then we used another sample of 80% of OPC and 20% of fly ash. Then another batch was prepared for 30% of fly ash and 70% of OPC, and again 40% of fly ash and 60% of OPC, and we tried up till 50 also. Though commercially we don't get 50 or PPC sample, which is PPC cement, which is available commercially in the market, that will contain maximum of 45 to 40% of fly ash. But we tried up till 50 to have an idea that whether the increase of fly ash concentration is increasing the level of radioactivity or not. And we repeated the protocols or processes which I have already mentioned in our previous slide, that we grind those materials, then sieve those materials from 150 micrometer mesh size. Then we removed the moisture by keeping those samples in an oven at around 100 degree, 110 degree Celsius for 2 hours. Then we packed those samples for 1 month to attain the radioactive equilibrium. And even yesterday I was discussing this, these containers are very specific for a particular detector. Means if your detector gets changed, the geometry of the container will change. If your geometry gets changed, the detection limits of the detector will change. So you should be very particular to have a similar geometry, similar dimensions of the container while packing your samples, so that the impact of geometry doesn't play any role in changing the readings. So your instrument is calibrated for a particular geometry. So calibrations are very important. So especially the PhD students who are pursuing their research, I would like to suggest them, while you are performing some of the experiments on the instruments, it is very important to do the calibration every time you perform an experiment. It is not possible for every instrument that you perform calibration every time, but if it is possible, you perform the maximum calibrations. Because if you are good enough in calibration, so you can have an idea by seeing the peaks or gamma peaks, that what type of material it could have. So that is very important. So then we studied those samples, and finally we found some of the concentrations of radium, thorium and potassium. Now details we will be discussing how to measure the radium, thorium and potassium. concentrations. We are not presenting it right now in this presentation because it is a gamma ray spectrometry technique, which is again contains a full lecture. So you could see that when I was showing you, this is a peak. So we have to calculate the area under this peak. Now, to calculate area under the peak, you should know that what type of software you are using, and your software should be capable enough to calculate the area under the peak. And based upon the area under the peaks, you calculate the number of counts per second. Then for every type of energy, there is a different efficiency of that detector, and for every different energy there is a different branching intensity of that detector. So there are two important parameters which one should remember, that your detector cannot be having similar efficiency for all the energy values. If you are measuring energy 609 keV, the efficiency of the same detector will be different for measuring the energy of 1461 keV. So once you measure, you should either devise a software which is nowadays provided by the company itself who are supplying these instruments. But as a physicist, you should know what is the particular efficiency for that particular energy which I am measuring for my instrument, and what is the branching intensity linked with that particular energy which I am measuring for my instrument. Suppose I am going to measure potassium. So I will look for 1461 keV of peak. And if I am getting a peak of 1461 keV, that means potassium is present. Now for that particular potassium, I should know from this y-axis, that is the counts per second. I would calculate the area under the peak to have a total counts per second, which even manually I could perform, or nowadays generally PhD students don't prefer to perform the manually curve fitting parameters. They are not interested in doing a lot of mathematics of calculations of FWHM values, full width, half maximum values, but you could perform it. And you should know it as a physicist also, that how the area under the peak is being calculated by the software. Though the softwares are capable enough to give you the direct values of concentration of radium, concentration of thorium, concentration of potassium, but you should know that what type of peak I am focusing for potassium, what type of peaks I am focusing for thorium, what types of peaks I am focusing for radium. So depending upon those peaks, if you apply your results, you calculate the concentration of radium, thorium and potassium. Then after calculation of radium, thorium and potassium from different samples, what we do, that we calculate the total radium equivalent activity. Now, the total radium equivalent activity means we convert the concentration of thorium into the equivalent concentration of radium, and we again convert the concentration of potassium into equivalent concentration of radium. And this is a standard formula which is given as radium equivalent is equals to concentration of radium plus 1.43 concentration of thorium plus 0.07 concentration of potassium. Now, from where these parameters 1.43 and 0.07 are there, the answer to this query is, it has been assumed that 370 becquerel per kg of radium or 259 becquerel per kg of thorium or 4810 becquerel per kg of potassium produces the same gamma doses rate. Now, as we are using the gamma ray spectrometry, so with this equivalent gamma dose rate, if you divide 370 with 259, you will get a parameter of 1.43. So that means you have converted the concentration of thorium into the concentration of radium. So the second term in this equation is again the concentration of radium calculated from the concentration of thorium. And if you divide 370 with 4810, if you divide concentration of thorium radium with 4810, you will get a value 0.06. That is the concentration of radium in terms of concentration of potassium. So what we have done, we have converted the concentration of thorium into the concentration of radium by using a parameter 1.43 times, and we have converted the concentration of potassium into the concentration of radium by using a parameter of 0.07 factor. The reason is 370 becquerel per kg of radium gives you the same gamma dose as is given by 259 becquerel per kg of thorium and 4810 becquerel per kg of potassium. So we make this parameter as a radium equivalent. So depending upon this radium equivalent, so if acceptable limits are 370 as far as organizations of economic cooperation and development is concerned. So if your soil's radium equivalent activity is more than 370 becquerel per kg, that means your soil is not fit for any construction purposes, for any use. So it will give you a very enhanced level of radioactivity. Then based upon the concentration of radium and thorium and potassium, we again get the doses, air absorbed doses. So this dose is calculated in terms of nanogray per hour. Yesterday, I have told you with the example of one tree and a passenger sitting beneath the tree, that once we use the absorbed doses, we use a parameter called gray, and once we calculate the effective doses, we use a parameter called impact of those absorbed doses, that is CVET. So depending upon different parameters, so the doses are being calculated from the concentration of radium, thorium and potassium, and then Indian and global average values of the absorbed doses rates is 90 nanogray per hour and 86 nanogray per hour as reported by the UNSCARE 2000. So for Indian standards, it is 90 nanogray per hour. For global average, it is 86 nanogray per hour. Then from these doses, we could calculate the annual effective doses in terms of sieverts or millisieverts, which I was discussing, that is impact of those doses. Now, if you see the two equations for indoor and outdoor, they are very similar equations. For 1 year, 8760 hours we have taken, and this is the dose conversion factor, that is 0.7 we have taken in both the cases. But in indoor, we have given a parameter of 0.8, that because 80% outdoor occupancy and 20% of indoor occupancy gives you this result. So for outdoors, it is 0.2. So then the annual effective doses you could calculate by using these two formulas, and finally you could have an idea that what is the effective dose given to a resident from that particular soil. Similarly, you could calculate the excess lifetime cancer risk from those AED annual effective doses, but you have to multiply those AEDs with some risk factors and the time durations. So if you take an average life of a human being as a 70 years and risk factor is 0.05 per CVET, so you could calculate ELCR also. So that is, of course, a basic idea. It's not a standard value which you will be getting. The reason is because excess lifetime cancer risk is by other exposures also. So if you are under some medication, then your exposure will be different. It is only due to the soil which we are calculating. Similarly, you could calculate the external and the internal hazard index parameters. And if you see the external and internal hazard index parameters, every time the hazard index parameters, due to the concentration of radon, T is 70 years. There was a question. T is generally on an average 70. This is the standard which has been taken by the UNSCARE. For Indian parameter, it could change. So external and internal hazard index you could calculate, and it should be less than unity to have a very lesser risk. And depending upon the same value, that is 370 becquerel per kg of radium, 559 becquerel per kg of thorium, and 4810 becquerel per kg of potassium, gives you the same gamma dose rate. So we have calculated the external hazard index. For internal hazard index, the concentration of radon is half, or radium is half, that is CRA divided by 185. But for thorium it is again 259, for it is 4810. So these are the two equations which you could remember for calculating the external as well as the internal hazard index parameters. Then depending upon our radionuclides, this we have calculated. Then annual nodal dose effects you could also calculate with the help of concentration of radium, thorium, and potassium. And UNSCARE has given a gonadal dose effect also. Value is you could calculate with the concentration of activity concentration of radium, thorium, as well as potassium. So these were our results. So if you see from the results, once we tried for different batches, we started with 100% OPC with 0% fly ash. Our radium concentration was nearly 27, thorium was 20, and potassium was 2000 roughly. Then we increased the fly ash parameter to 10% by weight and 90% OPC. Then for a same sample mass, the value of radium increased to 32. From 27 it increased to 32.52. Similarly, there is an increase in the thorium also. And then we go on increasing the concentration 70 30, 60 40, 50 50. And then finally the total fly ash. And you could see that the radium equivalent activity increases from 26.79 to 81.79. And similarly, the thorium concentration increases from 20.31 to 76.54. And similarly, there is a not so much change in the potassium levels. So it remains nearly of a similar trend. But this average radium equivalent, if you see from this column, the radium equivalent 195.6 becquerel per kg enhances to 274.02 becquerel per kg with the 50% mixing of fly ash with the cement. So there is a big enhancement. Similarly, if you see the hazard index, because most of the cements are used in the indoors also, so it is nearly touching the 0.95, that is nearly touching the unity parameter. So that is why, that is the con of use of fly ash in the cements. So instead of pros which we were discussing, there is a con also. And this graphs gives you an idea about that how radium and thorium has changed its concentration with the change of level of fly ash in the samples. Now, if you conclude it, of course, in most of the cases, it has been assumed that our samples are giving us a very lesser exposure as compared to the unity. A hazard index is less than unity, but the content of fly ash gives you enhanced level of radioactivity. And similarly, annual nodal effective dose for most samples, that is up to 30% of fly ash in post-landing Portland cement, fell below the recommended action level. But if you go with the more enhanced concentration of beyond 30%, it is more than the upper dose limits. So in Indian standards, generally 40 to 45% of fly ash is being mixed. But if you go beyond 40, it is little bit on a dangerous level. So what I would suggest from our case studies or our studies, that government should think of other parameters, that how they could advise the cement companies to use the fly ash up till the maximum level of 40. So that is very important. And another parameter is like which we have discussed. On the one hand side, we are saying that we are increasing the binding capacity of cement with the choice of the fly ash. On the other hand side, we are giving an enhanced level of radioactivity to the human population with the use of fly ash in the cement. So to conclude, I would say that in most of the cases, the concentration increases with the increased level of fly ash. But in case of potassium, the concentration remains unchanged. So both radium and thorium plays a very important role. And if you go up till 40%, your internal and external hazard index tries to touches the unity parameter or unity value. So it is then a cause of concern that how much we should mix the fly ash in the cement. So generally, from our studies, we could conclude that the maximum ceiling should be on the 40 or rather on the lesser side. But if you increase it beyond 40% by weight, the internal hazard index plays a very important role. So these are the few articles which we published, and this was a report: cement containing fly ash can cause lung cancer. So we have published this report with the help of our civil engineering group and my PhD students. So we have done some concrete results on OPC as well as on the PPC of different cement companies. So these are again, the talk is open for discussion now. So if any queries or any question is there, you could always ask. So there were few questions which were written in the chat box. Sir, please let me know how to learn and remember these units regarding radiations. Of course, once you will do the research and continuously go on reading some of the units. So like yesterday, I have given you one example that you could use. Try to remember that why the gray is used. Gray is used to calculate the absorbed doses. because I have shown you some passenger who was sitting beneath a tree और उसमें जो apple गिर रहे थे उसके ऊपर green color के थे. तो ultimately whatever the radiation is there, in suppose I am sitting in my room, so I can calculate the activity of my room, but depending upon how much time I spent in my room, that gives me absorbed doses. So you have to remember that what type of unit you have to use for what type of calculations. So it will enhance once you will do lot of research, because I have asked you that as a physicist, as a scientist, as a scientific temperament people, we should not restrict ourselves to only one parameter. Like I was saying that you have seen a gamma ray spectrograph. You should know that why I am calculating this result, whether I could calculate it manually also, because curve fitting softwares are being developed by some other people which might not be having a basic knowledge of basic physics, which you might be having. So if I am measuring say 186 keV of peak, I should know that 186 keV of peak is having this much of efficiency for this detector and this much of branching intensity. So branching intensity means how many gamma rays are being linked with that particular energy. So it is very important to understand. So sometimes in interview it is being asked that what is the efficiency of your detector. So people say, sir, it was around 70%. It cannot be same for every peak. For radium it will be different, for thorium it will be different, for potassium it will be different, for another energy parameter it will be different. So now the talk is open for discussion. Bhatti sir, namaskar.
Sir, I really enjoyed your lecture and it was very refreshing.
Thank you, sir. Thank you. So nice of you, sir.
Sir, being a civil engineer, Rohit sir,
encouraging.
Hanji.
You is always a encouraging stone for me.
Thank you, sir. Thank you. Thank you.
So if any queries are there, we
Sir,
are free.
Rohit sir, I have a small question. Like we have OPC, PPC cements, and we use PPC with, let's say, 30% content. And if we make some painting or some paints onto the walls, or do it affect the outcome in some way, protection to the human being?
No, sir. Actually, with the painting or coatings, the gamma rays actually they have a very high penetrating power, sir. So you cannot stop gamma rays to get out of the building materials by even if you place some tiles over those materials. So that is why I was telling you, because nowadays what is happening, the civil engineers are doing a different research, architects are using a different research, and we are doing a different type of research. So once we design a house, architect says we should use a granite in our house. As a radiation physicist, I would say the granite is having more radioactivity. And now ventilation conditions, you know, nowadays we are having closed kitchens instead of open kitchens. We are having glass all around, and even no ventilation is being provided. So that enhancement of different building materials and a choice of different building materials can enhance the concentration of natural radioactive exposures to the people working in those kitchens, in those environments. So that is why it is very important to have a basic understanding that what type of materials are giving me what type of radiations effects.
Excellent, excellent.
So nowadays we see that in India, mainly in our locality, people are making building with just as fly as bricks. So it is more harmful and dangerous.
That is what you see. This is a public platform where I can't openly say, but it's a policy of the government. The policy is not with the choice of fly ash brick. The policy is dumping of fly ash is the problem with the government. and they have come up with a solution. Okay, we will use the fly ash for making the bricks which are light in weight, even low cost, because fly ash is freely available. So
Yes.
government is ready to give you the fly ash. You can take your own truck and pick the fly ash from the thermal power plant. They will give you free of cost. The reason is the thermal is not a solution. So we have to look for some another energy
Some
sources,
energy.
preferably the nuclear sources. So that we could reduce the impact of our energy requirements on thermals. So now
Yes.
government is promoting solar energy as well as some other parameters, but solar is not the solution. So because our geological structure is such that everywhere we don't have a similar type of a wind uh, speed, and we can't go for even windmills, and we can't have a different type of a similar type of a solar panel availability, because it's a very costly affair.
Is
So
costly.
unless
Yes.
and until it is being manufactured in India, so till date it is very costly affair. Even we install our solar panels on our houses, the break even comes after 7 years or 8 years. So which is a very big lifespan. So and again at after 7 year it requires maintenance, battery are there. So again it's an environmental problem. So we have to accept that nuclear is the best solutions presently, which whatever the technologies are available.
As a researcher, we think in sitting India that we are in a safe zone, because the radiation level is quite lower in comparison to Europe, USA. But in next 10 years, the situation will be not like that, because
Definitely.
people are making a building with just of a fly ash bricks, and we are 80% of our lifespan is indoor. So
Ma'am,
we are.
and most important is like in South, especially the monazite is very high. If you see the Kerala sand beach, you will have a very high concentration of thorium. So, world's 97% thorium is present in India, and out of that 97% thorium, nearly 90% is present in that Kerala beach sands. So, it is it is a problem. So, is second is the thermal. It is again a problem. The dumping is a problem. So that is why what I am saying. The government has given you a solution, because they were having another problem, that how to dump it. So they have given ki okay, for fly ash brakes manufacturing industry we will be giving subsidy. So they are preparing it. Houses are being prepared. But if you have a annual effective dose calculations, those houses will be having more concentration of radioactivity.
And we are very few people who are doing this type of research in India. So people are more and more people have to come in this field, so that the radiation hazards awareness can
Yeah,
spread in the
definitely.
public. It is
That is
very,
what I
very
was saying,
necessary.
because we have never asked any radiologist, sir, I have been given an X-ray. How much exposure is given to me?
Yes.
There is a lot of guidelines which are written. So a pregnant lady should not go for 3 cycles of CT scans during a pregnancy cycle. What is the reason behind that? So
Yes.
we are not having a law in our country at present that I could ask the doctor. Even radiologist doesn't know. Radiologist doesn't know that this machine is giving this much of exposure. Some of the radiologists are very good enough, but some of the radiologists even doesn't know. So this is a
And
problem with 144. That is, our population is a bigger problem, because you can't make everyone aware about these things. But during these type of discussions, definitely we got some information. We pass on those informations to our neighbors, to our known people.
yes. And
Komal,
thanks
you
to
were asking
you
something.
for and thanks to
Yeah,
you for hosting such a GIAN program, so that more and more people can come
yeah.
to. do this
No,
kind of
we
research.
we are also very open for research also. You can always come to our laboratory. We are free to do the analysis for our collaborative people, and we do these type of sample studies. Like this was a a pilot project
Yes,
which
yes.
one of my MSc student has undertaken. So now he is pursuing research in NIT Kurukshetra. But we generally prefer these type of activities with the Department of Chemical Engineering, with the Department of Civil Engineering. So we go on doing these type of. We are also doing activities with the extraction of heavy metals from the water, which I was discussing yesterday,
Yes.
by developing some natural polymers. So as a researcher, one should take initiative.
Yes. Sure, sir. In future, I will go NIT Jalandhar to meet
Yeah,
you
sure. Thank you.
personally. Okay.
Most welcome. Most welcome.
Good evening, sir.
Good evening, Komal.
Yes, so actually, I was enjoying Professor Ankita's discussion with you, and that was really interesting. So, I want to today's session was on construction materials.
Yeah.
So, is there any study our group is doing on PVC tiles? That is also a big trend in house making nowadays. Doing construction with
Presently,
PVC
we are
tiles.
not doing any study on this area, but it is a very common. We could always do because we are having lot of instrumentation. If even
Yes, because
some of your
I have.
students are interested, you can go give those students the
Okay.
project like this, and they can come to our lab and do the studies, because techniques I have already mentioned. So you have to
Yes, sir.
prepare the sample
Yes,
as far as our
I am
material.
learning that online as well as personally. I am also discussing sometime. The thing is, because I have learned a lot of papers on different construction material regarding fly ash bricks and different kind of cements and all, but I have never heard of PVC. But some are saying that PVC tiles are also leading to certain kind of health hazards. So I want
Maybe
to convey that.
presently we have not conducted any study, so
Yes, sure.
I won't be in a position to answer it. But
Okay.
we could always conduct.
Sure, sir. We are planning to do that. Thank you, sir. Thank you.
Okay,
It is
madam.
nice talk. Otherwise.
God bless. So Abhishek, then I think we could conclude.
Yes, sir, we can conclude the session now. Thank you very much, Professor Rohit Mehra, sir, for such a detailed and comprehensive talk with so much clarity. Your expertise in the subject is always highly appreciated. So a reminder for the parents, for the participants, that attending the lectures, all the lectures is compulsory to be eligible for the award of certificate. So please attend all the lectures of the course. With this, we conclude today's session of this GIAN course. Thank you very much for your active participation, and we look forward to seeing you tomorrow for another engaging day of learning and discussions with the Professor Tokonami Sir's talk on dosimetry of radon. Thank you very much, everyone.
Thank you. Thank you. Okay.